Bart, we're here at the new AMF launch. What technology is on show?
So we've got a whole series of different technologies that we're here showing customers today. If we actually have a look over here on the left-hand side on our Huron machine, we're showing a really exciting piece of technology which enables customers to really rapidly program their jobs in 3-axis, the way they're familiar, happy, find really efficient ways of machining, and rapidly take those toolpaths and convert them into 5-axis. Now you might be asking, why would you take a 3-axis toolpath and convert it into 5-axis? Well, often we have geometries where we can get at the parts in 3-axis, but the geometry of our machine tool means that we'd need really, really long tools, which would obviously could result in chatter, really poor surface finish, and historically people have had to program them in 5-axis. What we're able to do is automatically convert just those regions of the toolpath which we need in 5-axis to enable us to get access, and leave the rest of the toolpath in 3-axis. We're doing it automatically in the software without the user having to do any real work at all.
Is that PowerMill?
That's in PowerMill in the 2019 version of the product, which is just being released now.
Okay, and the Hermley behind us, and there's a famous looking aerospace part on there.
Okay, so as well as getting involved in automotive projects, aerospace is an area where we have a great deal of knowledge and experience. And on the Hermley machine today, we actually have a blisk. Now a blisk is a combination of both a blade, or a series of blades, and a disc, which you're machining out of solid. In this case, we're machining them out of titanium. Now that makes the part much larger and much more complex in terms of manufacturing compared to independently machining the discs and the blade. But the reason that it's done is you get a product at the end of the exercise which has much better aerodynamic performance. Because it's got better aerodynamic performance, it's more fuel efficient when it's running in the engine, and that means we all get cheaper holiday flights when we go on holiday. So we've got an example there of a titanium blisk that we're machining at the moment. And not only are we machining those on the Hermley machine, but we're actually driving the whole of the manufacturing process using a new product, which is fusion production. What fusion production enables us to do is to take all of our assets, which are here in our advanced manufacturing facility, or they could be in facilities belonging to our suppliers. We're able to see all of our assets, we're able to send the instructions that are particular for the machine and the job we're doing, so all of the toolpaths in this case, and use fusion production to send that information out to the machine tool. Just as importantly, what we're then doing is we're actually capturing information about what the machine tool is actually doing, and then using that to inform future manufacturing operations. So for example, maybe when we've sent the machining instructions down to the machine, we're expecting it to take 2 hours to run. What we actually discover is that it's taken 2.5 hours, and we can then go back and we can look and see, has it taken 2.5 hours because the feed rates have been turned down on the machine, or is the accelerations and decelerations of the machine different to what we expected, or has the operator been for a quick coffee break halfway through the shift? So really powerful tool to enable us not only to manage our business, but to continually drive the improvement in the performance of our business. Okay,
so we're probably talking about IoT and things like that. It's a lot of data. Is that data secure?
Absolutely, that data is secure. We are actually storing all of that data on the cloud, but that data is completely secure and only accessible by the customer.
So more 5-axis technology, this time DMG Mori. What's on show?
Okay, so today we're actually programming some generatively designed components. So we've actually got an automotive upright, which has been designed using a traditional design process. We've ended up with a part which is relatively two-dimensional in its shape. What we've used is the latest of our generative design technology to actually produce a much more ergonomic shape, really looking at how we minimize the amount of material that's required in the component. But that creates us a whole series of manufacturing challenges. So we get a really interesting component from a design point of view, a really challenging component from a manufacturing point of view. So what we're doing is we're investigating how we can use manufacturing parameters to actually influence our generative design process so that we can come up with generative designs which are well suited to manufacturing. So here we're looking at a generative design which we're machining on a 5-axis machine, but similarly also looking at generative designs which we could machine purely on a 3-axis machine, or also in fact in 2 dimensions. So we can have a range of different complexity of products to meet the needs of different customers.
That's interesting, because this is normally a process you'd associate with additive manufacturing, but this is obviously subtractive manufacturing. I guess it's all about design for manufacture.
Well, it's all about getting the right solution for the particular application. So you can imagine if you've got a particular application, maybe you're wanting to produce a part for a Formula One car, and every gram really counts in the performance of that vehicle. And so you might go to producing something initially which is additive, and then maybe doing some subtractive operations on it. Maybe you're actually wanting a part which is maybe going to be for a premium product, so maybe it's going to be for your club motorsport vehicle that you're selling, and you're wanting something that steps away from the type of part that you might just see on a traditional vehicle. And so maybe having a part there which we've produced subtractively, but taking advantage of generative design is the way forward. Or maybe what we're wanting to do is to just look at improving the performance of a part that we're actually going to produce in real volume in the future. So really, again, different solutions to meet different customer needs whilst using the same core technology.
And you've also invested in a new Mazak. What technology is on show there?
Okay, so as well as recent investments in 5-axis machines, we've also been bringing in some more turn mill technology. Obviously, a whole series of different components that are ideally suited for turn mill platforms. And what we're really interested in doing is combining a lot of the technology that we have on our experience on the milling side and bringing that onto other platforms as well. So one of the key technologies that we're demonstrating today is actually our Vortex Technology. So how we can look to remove large amounts of material in a very efficient way on radial components, as well as components which we would typically see in a milled environment.
There's also a machine, the larger machine at the bottom there, where it looks like it's removing weld from a mold.
Okay, so a really interesting process here. So if we look at automotive tooling, or many other types of tooling, often we have to do repairs on tooling, or we may actually sometimes get tooling which has maybe been initially produced, it's maybe been run initially, some test parts have been produced, and people want to make alterations to those tooling. Now historically, the way people have done that is they have hand added maybe some weld to build up some more material, and then they've gone back and they've remachined that. But it's quite a risky process. In reality, you don't know exactly where the weld is that you've put down. So when you go to do the machining, it's not a very under control process. Now with the latest versions of Power Mill, we've been introducing the ability to actually drive direct energy deposition systems. So these are high rate additive platforms to control things like welding robots. So we can now use a programming system to lay down material. We know exactly where the material is, and then we can align that with our subtractive processes to remove that excess material and give us a new finished component. So really combining both additive and subtractive into the single Power Mill environment to enable customers to get better quality and much faster throughput where they need to do changes, alterations or repairs to tooling.
Well, you talk about additive manufacturing. I know we've got an exciting demonstration over there. Let's go and take a look.
Great, let's go down there.
Bart, I find this astonishing. This has actually been additive manufactured. Is it a game changer?
It's absolutely a game changer. Yep, so this has been produced using additive manufacturing. So we've used direct energy deposition to lay down a very large amount of material really, really rapidly. So using technology which is very close to a traditional welding robot, driving that welding robot to lay down material in really the reverse process of what we would normally do on a machine tool to add material. But by using a welding robot, we're able to achieve much higher material deposition rates than what you would traditionally see by most additive manufacturing processes.
What material?
Okay, so this is actually a bronze alloy. So like most ship propellers, produced out of a bronze material, very, very corrosive resistant, because obviously it spends its whole life in seawater, racing around and being in contact with all the things that you get in seawater.
And I would guess a vessel, the type of ship this is going to go on, you don't want those sat in the dock, do you?
No, absolutely not. So if you think about a really big container ship, the ships that enable us to get all of our products rapidly around the world at really, really low cost. If one of those is actually stuck in a container port, maybe it's had some kind of damage to the propeller, it could cost as much as $200,000 a day for that boat to be sat in port waiting for a replacement component.
And how long would that be using traditional techniques?
Well, it's a really big challenge. You imagine traditionally a component like this, the component would be cast, there'd then be either grinding or finishing operations to get the finished shape, probably have to go to a specialist manufacturer who could be in another part of the world. So you could be looking at a very long lead time, or you could be the terrible situation where you actually have to have in your stores a whole series of propellers or other components just in case they break.
And I know this is 400 kilos. It's going to be expensive. I don't want this in stock, do I?
No, absolutely not. Having a whole series of these components of different sizes sat in stock, there's actually research which says as many as 80% of the items which are sat in stock never get consumed. So they're items which have been put into stock just in case they're required for a component which breaks, and they're never used.
In the additive manufacturing environment, we see lots of products that look great, but not necessarily in a commercial environment. Is this available?
Yes, so this is available within our products today, the capability to drive direct energy deposition systems, whether they're robot-based, whether they're machine tool-based, to enable people to control their machines to produce these types of components. It's definitely at the explorative stage for many organizations, but the technology is available here. Now we're looking at it in terms of a ship propeller, but exactly the same technology we're using to drive processes such as repair on mold tools. So the technology is really applicable to a broad area of industry today.
Autodesk, you must have a very happy partner here.
We do have a really happy partner here. We've been working with the Port of Rotterdam as part of the RAM Lab project, and we've had a great partnership with them to develop the manufacturing technology and actually produce some of these first components. And this component's actually been stamped by Lloyd's Shipping Registry to confirm that this product is of the correct quality to enable it to be used in a ship. And this particular component here has actually run on a ship in the Port of Rotterdam, and we've actually had it back off to have it checked and confirmed that it's in great condition, and it's actually here for us to see today.
So we've got a clay milling application here. What products are involved?
Okay, so here we're using both Power Mill and Power Inspect for this clay milling application. So we have a Stiefelmeyer machine here. The Stiefelmeyer machine is used in automotive styling studios around the world, so all of the big brand names you can think of here in the United Kingdom, in Germany, across Europe and the United States. Clay model styling is a really, really important process for automotive manufacturers. In reality today, we all expect our cars to be super reliable, have lots of technology on board. Really the key differentiator for most automotive brands is the styling. Okay, so the ability to produce a range of different styles, to take those designs, make alterations to them, rapidly iterate and produce new designs is really, really key. So here at Autodesk, we're able to take design tools such as Alias to come up with new conceptual designs, rapidly produce clay models. The artists, the stylists, they want to be able to see the physical models, they want to be able to make hand alterations on the physical models, and then they want to be able to capture information and take it back to their design system to go on to engineering. So that's the complete process we support.
Yeah, I was going to say that, Autodesk being Autodesk, everything from the concept through to reality.
Yep, so we're looking at tools like Alias for doing the conceptual designs. We're looking at products like VRED, which not only enable us to produce the realistic renderings of what the final vehicle will look like, but actually enable us to take those designs and place them into an environment and drive through them and produce, for example, the adverts that you see on TV for a car, which incredibly are actually produced before the car's made.
So far on the tour of the AMF, we've seen subtractive manufacturing, we've seen additive manufacturing, now we have both all in one cell.
Absolutely. So another one of our partners here is Hamul. We're working with them to develop the manufacturing processes required to drive some of the next generation of machines which contain both additive and subtractive in a single platform. So that creates particular requirements for us, great opportunities to interleave, so the idea that you do a bit of additive, a bit of subtractive, a bit of additive, a bit of subtractive, and really build up some unique designs. So yep, working with Hamul to develop those manufacturing processes to really support this new generation of hardware that's becoming available.
Bart, this is something I thought I'd never see. Augmented reality in a manufacturing environment. Incredible.
It's a really interesting and exciting area. Augmented reality, not just in the concept of the project that we're going to talk about here, but also in some of the other areas that we're working. But we'll talk a little bit about this project first and then maybe touch on some of those other topics next.
Okay, what do we see behind us? Okay,
so one of the activities that many people aren't aware of is the amount of polishing that still goes on in our industry. So a lot of tooling to get the required finish that's required. There are polishing processes. Today, those polishing processes are largely manual processes. People are in there with wet and dry, a whole series of other techniques to get the surface finish that they really want to get. So what we've introduced initially is the ability to use robotic solutions with particular end effectors to actually go in and polish the surface of our tooling. But what you need to do as part of that process when you're polishing it is also then to scan that surface, to understand what surface finish you're achieving, and be able to go back and make those iterative decisions about whether or not there's more polishing you need to do, or whether you've done enough. And augmented reality is a great way of providing the operators with additional information in real time about the surface finish that we're achieving on this job, now on this machine.
So we've got not only augmented reality, but we've got the automation.
Yep.
It's reducing the need for human intervention. People talk about automation losing jobs. You're probably going to upskill this individual, aren't you, to a better job?
So absolutely, what we're doing is we're removing what's a sort of a dirty and manual process, and we're introducing it with a process which is repeatable, it's scalable, it's much cleaner, much better working environment. It doesn't remove the people from the process, it removes the people from having to do the filthy part of the process.
So how long will this be until we see this in the field?
Well, this is a research project, part of the Simplicity European funded project at the moment. So at this stage, it's something that we're still collaborating with partners, and so we don't have a formal launch date for this technology, but we see opportunities for this technology, not just here in the polishing environment, but in a huge range of other applications. So for example, in the traditional machine tool applications, obviously we load material in, we put the tooling into the machine tool. It's very easy for small errors to be introduced. So for example, somebody to use a tool which is too long or too short. So imagine being able to use augmented reality to actually see exactly what tool should be in the machine next to the machine next to the tool which is in the machine for a quick visual check. We want to be able to provide the user with additional information, such as on the speeds and the feeds that we're using, all within an environment where it's adding to what they do today.
It's an incredible facility with lots of different processes. Do you have a favourite, Bart?
Well, modern manufacturing is about combining technologies, and that's what we do here today. So we've shown you additive platforms, we've shown you subtractive platforms, we've shown you metrology equipment, we've shown you platforms driving robots, platforms where we've combined additive and subtractive into a single platform to enable our customers to make anything.